Hello everyone. So today we'll be looking at this question called binomial coefficients. So the problem says that you have to calculate n binomial coefficients and you have to bring the results modulo 10 power 9 plus 7. Right. Okay. So for those who I hope everybody is aware of this simple formula that how do you calculate a choose b? It's simply a factorial upon b factorial into a minus b factorial. Right. So we need to calculate this thing mod some value which is 10 power 9 plus 7 and just return whatever we get, right? And we have 10 power 5 such cases, so that means that at least 10 power 5 times I have to run the loop, so which means that I need to compute my binomial coefficients really fast, right? So for that, uh, an idea is like, if I just show you one thing, that see the limit for a and b, the limit is 10 power 6, right? It is 1 6. So be it a factorial, be it b factorial, or be it a minus b factorial, all of that is going to be within 10 power 6, right? So I mean, like a minus b, a and b, these values are going to be between 10 power 6, right? So what I can do is I can pre-compute a factorial array, right, which will take 10 power 6 time, because let's say if I assign uh, factorial of 0 we know is 1, so what I can do is I can do it this way, that I can just assign factorial of 0 equal to 1 and then run a loop O of n complexity loop, right? So it will run for 10 power 6 iterations and give me whatever it is. So I'll just define some variable max and I'll assign that one 6 plus 1, and I'll make an array which will have all the pre-computed factorials. So there's going to be something like this, and now I'll simply do this, and for int I equal to 1, I less than equal to n, I plus plus, I'll simply assign factorial of I equal to factorial of I minus 1 into I. Right, so this helps me to pre-compute all the factorials that I have. Right, but one thing that's important is I need to take modulo, because otherwise it's going to overflow. This 10 power 6 factorial is going to be really large, it will not fit in, and then, right? So what I can do is, yeah, I've already defined const ln mod. Okay, so now the question is about how can I do this thing. Like, I need to print modulo of this value, no? So I need to compute a factorial upon b factorial and a minus b factorial modulo m, right? So you can very well see that, let's say, just tell you, if I just give you an example. So if I just tell you to calculate x upon y, this thing mod m, so what you will do is you will take x mod m into modular inverse of y, right? So I'll need modular inverse of y. So what so from Fermat's theorem we know that a to the power p minus 1 is 1 mod p, and what is multiplicative, what is this modular inverse? So if I have some a into x, if I have some a into x that is congruent to 1 mod p, so my x is the modular inverse of a, right? So from there, see this one, this is from Fermat's theorem. This is called Fermat's theorem, Fermat's little theorem, where I know that a power p minus 1 is 1 mod p. So now I can just break a to the power p minus 1 as a into a to the power p minus 2, and this is also equal to 1 mod p. So that means that multiplicative inverse of a is a to the power p minus 2, right? So uh, here, for this particular thing that I need to compute, that is a factorial upon b factorial into a minus b factorial. So for b factorial, like taking its modular inverse, you will simply multiply this with. So the end result is going to be somewhat like this, that you will have a factorial into b factorial modular inverse of it, which is going to be b factorial to the power b minus 2 multiplied by a minus b factorial. This thing again to the power b minus 2, because we are also taking inverse of it, right? So this is the end result that I need to calculate, right? So now the point is I need b factorial to the power b minus 2. So b factorial I can simply get from my pre-computed factorial array that I've calculated. But getting the power in p minus, like getting p minus 2 power where p is 1e9 plus 7, so that's really large. So for that I'll be using this function. So I've copied it. I've already made a video on modular exponentiation, so this uses modular exponentiation, right? So I've made a video, but I'll just explain in short what we do in modular exponentiation. So what we do is, let's say we are computing a to the power b. So we keep on dividing b divided by 2, and we keep dividing it till the time b is greater than 0, right? So it's something like this, that if you have to calculate 4 power 4, so we are dividing the power by 2 and squaring the base. So 4 power 4 is 16 square, right? And then again 16 square is 256 to the power 1, and so that way it continues, right? So till your b is greater than 0, that time will compute. And so what you can realize is, what this binary exponentiation helps us in is that it increases the base and it reduces the powers, right? So as it reduces the power, so what it is helping me is reducing the number of iterations as a result of it, right? So modular exponentiation is generally, the complexity for modular exponentiation is going to be, I've told all of this in my last video, but it's going to be O log B. It's going to be O of log B. So each power I can compute in O of log B, and for the factorial thing, I'm taking O of n, right? O of 1 e6 actually, right? So that is very much feasible in whatever time complexity we have here. So this is your power function, right? From here, I've already got my factorial array pre-computed, and then I'll take input of n, and then what I can do is, for all the n cases that I'm going to have, I'll take a and b as input, and then I simply define some result. Now, okay, so once I've defined my result, I'll simply have to multiply. First, I'll multiply my result with result into fact of a. This thing I have to do mod, and then I'll again do result equal to result into fact of b. But not only fact of b, I have to also, like, I have to write a function that is power of fact of b comma b minus 2, and I'll take the mod of this whole thing. And finally, let me just copy this thing. So instead of factorial b, I just have a minus b now, right? Okay. So that's it. And finally, I just need to see out my result, right? Okay. So I hope that that was easy. Let me just see if there are any bugs in the code, and let me just try to execute this once. Okay, there's something wrong. Okay, okay. So p is not defined actually, because I showed the example with p, so I wrote p here, but I need to write mod because I've defined it as mod. So now I'll just copy this. Still some error. I less than equal to n, there's an error. I less than equal to, na? Okay, okay, see. This loop I just need to run for max plus 1, right? No, max is enough, no? Yeah, max is not even enough. Because 1 is 6 plus 1 is the limit, so yeah, max is going to be enough. So yeah, now this should work. Now let's see if it works. Yeah, so output is correct. It's 10, 8, and 126, which means this whole code is correct. So I'll just summarize it just a bit, whatever I did. So all that I did was quite simple. I just used model exponentiation to calculate the powers, and the basic part was calculating A choose B quickly. So that was done. Like the main part was about taking the modulo thing. So the modulus comes from this Fermat's theorem. You can just go through this to understand it, and if you don't understand it, you can just post, you can just write it in the comments. Thank you.